So once again, hello everybody. Really happy to meet all of you. I'll try to present my first place solo solution. First of all, my name is Ilya. Just like few words about myself. I'm currently living in Batumi, which is in Georgia, on the seashore of the Black Sea, which is in Europe. I'm working as a lead data scientist at Stellanos. It's a small US-based data consulting company. I have some background in fundamental science. I was studying different mechanisms of redox regulation in plant cells. Was working as a research fellow in our state university, but long ago, like almost 7 years ago, have switched my working field to data science. So just a small summary of the competition of my solution. So as we remember, the task was to classify histologically confirmed cases of skin cancer. We have both image data and tabular data. And one of the main issues from my point of view was that the dataset was kind of highly imbalanced. We have just a few hundreds of positive cases. And later I will describe how I have handled it. I've joined this competition roughly like 4 weeks before the end. So at this moment, there were already some good public canals, which I have used as a starting point. My final solution was an ensemble of 150 GPT models, which were trained on tabular features, including some features extracted with NN models from the images. I've also used some external data based on ISIC archive. And one of the most important, from my point of view, parts of my solution was the way how I have measured my experiments. So first of all, as I guess most of the competitors here, I've used stratified group scaffold, group on patient level. But due to high imbalance of the data, metrics were quite noisy. So I've decided to use approach which was proposed, I believe, like 5 years ago in Mercedes-Benz competition. So the key idea was to run cross-validation multiple times. In my case, I was using 5-fold group scaffold. So I've run it 10 times with different seeds, which give us 50 different metric values, and for them we simply apply the tests to compare current score distribution with the original distribution before the improvements. And if p-value is below the threshold, in my case it was as usual 0.05. In some cases, in some experiments, I increased it to 0.1. So only in this case the improvements were used, otherwise they were rejected. And also, because we do not handle a multiple comparison problem here, I tried not to make too many comparisons and try to test only the most valuable ideas from my perspective. The last but not the least part is synthetical data. I didn't use them in final submission, but I've spent like most of the time, actually about half of the time for this competition for synthetical data. I'll describe it a bit later. So let's start from the solution overview. So as I've mentioned, we have image data. For image data, I've trained 2 architectures. It was EVA second version small and HNext base. They were trained on cross-validation with 5 folds. So each model is trained on 4 folds, while validating on the fixed fold with early stopping. After run this for all of the folds, we get out-of-fold predictions for the whole data set. And these predictions are used to enrich the final feature vector. So we get these predictions for EVA model and for HNext model. Also, as I've said, we have just like a few hundreds of samples of positive class. That's why I believe that enriching this data set with some other data set which have more positive cases like ISIC archive may bring us some benefits. So I've tried to train a different feature extractor on ISIC archive data. Of course, the distribution of these images in this competition differs significantly. That's why this feature extractor does not perform well as it is on this competition data, but as a feature extractor, as a part of the final vector, it brings some improvements. I've tested it both on cross-validation, on public and private leaderboards. In all the times, it was quite stable and significant improvement. Also for tabular data, actually, I've used most of the features of the public notebook. I just ran some feature elimination procedures, reduced the number of features to about 200, and also did some small feature engineering things. Most of my experiments were not successful. I mean, based on t-test comparison, I didn't find any significant improvements. There were just few exceptions, and one of the main exceptions was local outlier factor. So actually, we have lots of features which are norms on patient level, which I believe help us to find out that this, let's say, mole in terms of distribution for this patient is some kind of abnormal. But I think it's not. It doesn't fully describe the whole picture. So I decided to calculate outlier factor based on the most important features in terms of usage by the model. So we just simply took top 20 features which result in most gain for GBM model, and use them for calculating of log. And it was kind of beneficial because both on CV and on public-private leaderboards, it results in significant improvement. And the second part was just using of random override node sampling, just as in public notebook. And I didn't spend much time experimenting here, just took it as it is, because most of the time was playing with synthetical data, actually. So for each of the models, we run cross-validation with 5 folds, and we do it 10 times with different seeds. It results in 50 models per model type, so in total 150 models. After that, we simply ranking their predictions just to overcome the potential differences in distribution and simply average. And here's the final score. Just a few words about the top features. As you can see here, you can see here for permutation feature importance. It's not the best way, of course, to show feature importance, but I get stuck a bit to permutation feature importance. It's very useful in most of my projects and experiments. In terms of shape values, the picture is pretty similar. So the most important features are based on separate feature structures like EVA and EdgeNext. You can see them on top. I'm not very good at naming, so naming is not very intuitive here. The fourth feature is OF. It stands for outlier factor. Very high and very stable impact on the model predictions. Also for predictions based on visual models, I've also tried to calculate some kinds of normalized prediction patient level. You can see them here as score mean temper. It's simply normalized prediction for this model, normalized by the overall predictions for this patient. And some features like alt set 0, it actually stands for normal Nevus class prediction based on ISIC archive data. So as a second part, I would like to stop a bit on synthetical data. I really spent lots of time playing with them. Unfortunately, didn't get any high improvements on the public leaderboards with them. That's why my final solution didn't use them. But one of my best solutions, based on the private leaderboard, actually was based on synthetical data. So there are some papers describing generating synthetical data for skin cancer. One of them was DermTextIm. So I've tried to replicate it. Here you can see some examples of positive class from the competition dataset. Some malignant moles generated using the model from this paper. The model is public. You can find it on Hugging Face. And I've tried to train Stable Diffusion 1.5 model, one of actual fine-tunes of this 1.5 version with competition data. So competition data are not in high resolution. That's why I've been training the model in low resolution, 128 pixels square, and actually generating output images in high resolution because it worked a bit better. I'm not really a dermatologist. It's tricky for me to classify if it looks like a malignant or not. But some experiments, like I've been fine-tuning vision model purely based on synthetical data, and it shows that results which we get on synthetical data only is just the same, almost the same as based on computational data. So I do believe that they may look similar, but better to ask some dermatologists. So in my experiments, when generating statistical data, I've also been doing some cross-validation splitting. As is shown on this example, we do split on the 5 folds, as the model is trained only on these 4 folds. while generating predictions, while generating synthetical data, will be used to train a visual model, which will be using this again positive samples from these 4 folds and synthetical data. And so only after that, it will be used to predict for the 5th fold. It's done in this way just to reduce the potential data leak, because in some papers, actually, as the models were trained, especially in this one, they were trained on the full subset of the data, including the test data, which results in some over-optimistic estimations. In total, I generated around 6,000 of synthetic images, which were used along with real positive samples. And I did some measurements with HNext model, comparing model performance on cross-validation, also on private and public leaderboards. Here you can see average prediction for 5-fold models. It means that I've made for private scoring, I made 5 different submissions. Within each submission, the model was trained on 4 folds from these 5 on group fold. And you can see that an average model with synthetical data performs slightly better, actually. But as a part of my final ensemble, on cross-validation, it was slightly better, but in public leaderboard, it was slightly worse. So that's why I decided not to include it. The public leaderboard score you can see here, but actually the private one was much, much better than the one I actually got. Also, one note, one interesting finding here was that while training in low resolution, model generalized, and then vision model generalized much better in case if synthetical examples were generated in a bit higher resolution and then downsampled to a lower resolution, comparing to the case when synthetical data were generated originally in low resolution. Also, there are some issues which I didn't manage to resolve by the competition. In some cases, synthetical data generated didn't show any moles at all. Some of them were showing moles which I would prefer to call not malignant. I'm not a specialist, so maybe some kind of extra filtering should be applied on top of that. Also, as I've said, I was training SD models purely on positive cases. I've also tried to train them on hard positive cases because some positive cases were quite tricky to predict correctly with vision models, and I believe that maybe augmenting this part of the data sets may result in some benefits. But unfortunately, model generalization was much worse when training SD models only on hard positive samples. So. Small overview of the overall solution. Overall training time was around 36 hours. I had a small cluster with one single ISIC 1000 GPU. Most of this time is actually spent on vision models training. Ensemble of GPT models, overall 150 models was trained within like 20 minutes. So actually we can even increase maybe this number, but actually I've also experimented decreasing the number of final GPT models to 45, and the score was almost the same. So I just kept 150 GPT models at the end because it was quite cheap in terms of computations and was kind of affordable from my perspective. Also, usage of synthetic data, it's increases overall runtime, not runtime, but training time by 10 hours because on train SD models on 5 folds, it took roughly like 30 minutes for each repetition, plus generation of that many statistical images is also time consuming. A few notes about evaluations. As I've said, I've performed specific strategy with cross-validation to test for simple NN-based experiments because NN training for 1 fold, in my case, it was for HNext about 2 hours. I used a bit different strategy. I was first training a model on 1 single fold, evaluating its performance on 1 single fold after modifications. If there were any improvements there, I also tested it on 5 folds, just pure NN testing. And only if it worked, only after that, I did cross-validation tests. It reduced the number of experiments actually tested with this strategy, and unfortunately, reduce the number of hypotheses which actually results in any improvements. So another important thing here is that as neural networks. They were trained with Ilya stopping for roughly around 200 epochs. For Ilya stopping, I used holdout set. So it results in some. I believe it results in some kind of data leak. So to prevent to eliminate the data leak, I also added some kind of small noise for dataset during training of GPT models. The noise was added purely to NN predictions, only to NN trained on competition data. NN trained on ISIC archive data was kept the same. So a few notes about augmentations and different stuff. Augmentations I took actually from the previous competition as it is. I did some experiments, but realized that I do not expect high improvements. My highest expectations were on synthetical data. That's why I didn't make much experiments with augmentations. I did some kind of simple balancing when training the nets, balanced positive and negative class in equal proportion. And due to the fact that I have been testing on the whole validation fault, the number of samples, of course, in validation fault and in one training epoch differs significantly. In training epoch, it was much smaller. That's why initially the frequency of testing on validation data was testing every 5 epochs. Then it was decreasing to every 4 epochs and so on and so on. While getting to 100 plus epochs of training, testing was done almost every epoch. It reduced the training time significantly. There were a bunch of ideas which I actually tested initially and it didn't work. I've tried to apply different weighting strategy for negative samples because we do have lots of negative samples, and some of them actually hard negatives. They look just the same as almost the same, at least for me and for model, almost the same as positive class samples. So I tried to sample them during training so that hard negative samples appear a bit more frequently. I did that based on model error on these samples, based on out-of-fault model error. But that didn't result in much of improvement. So this idea was rejected at the stage of 5-fold training with the next model. Also, I've tried different architectures. It seems like HNX and EVA were suboptimal choices because my experiments, for example, with efficient net showed slightly worse performance. The same applies for a bit bigger models. I've tried a bit bigger versions of EVA, but performance was significantly worse. And that's it. I think time for questions. I've tried to be brief.